Hello and welcome to another edition of TutorTube, where the Learning Center's lead tutors help you understand challenging course concepts with easy-to-understand videos. My name's Ebby, lead tutor for math and political science. In today's video, we will cover integration by parts. Let's get started. Before beginning the integration by parts process, let's try some quick examples. In the first example, we will use the U-sub method because we have a function and its derivative represented in the integral. To make that clearer to see, let's rewrite the integral like this. Now we can take u as ln and du its derivative as 1 over x dx. And the integral will change to this once we apply. Now we will apply the reverse power rule to evaluate the integral, where we add 1 to the exponent and divide by what we added. Then put it back in terms of x by using the original u substitution. For the second example, we have to determine the trig value whose derivative is cosine. And because of the chain rule, we would have to divide by the derivative of the argument. Since the derivative of sine is cosine, the integral of cosine, which is essentially the reverse process, will be sine. Then we will have to divide by 2. So essentially, our answer is going to be the reverse sine, and then we have to divide by 2 because of chain rule. Now the third example, to solve this one, we will also use the u-sub method. In this case, let's take u as x minus 5, and its derivative would just be dx. The new integral will now be this. Notice we have an extra variable that's not in terms of u, so use the original u substitution, u equals x minus 5, and solve for x to make it in terms of u. So use the original substitution, and then plug it back in. Now let's deal with the new bounds, u of 5 and u of 7. U of 5, we use the original substitution as well, and we get 5 minus 5 when we plug in 5. U of 7, we would also plug in 7, so 7 minus 5 will get us 2. These are the new bounds, and this is the new integral. Now we simplify by distributing, apply the reverse power rule, and finally apply the fundamental theorem of calculus, which will get you about 11.61. Okay, now that we've done some important integration examples, let's take a look specifically at integration by parts. Integration by parts is basically the process of finding the antiderivative, like we were doing before, but it's a different way. In this method, we're essentially reversing the product rule, sort of splitting up the function and performing a special formula in order to solve the problem. The special formula is uv minus the integral of v du written here. And we utilize a hierarchical method that will tell us the best choice for u. Because similar to u-sub method, we have to pick a u first. Let's use these two things to solve this integral. This integral can be rewritten as this. Using the hierarchical method of establishing what exactly the functions of the integral are, ln x is the logarithmic function, so that's going to be the first thing or the best choice for u. We take the du of that. Now, we have to get the rest of the function because there's still another ln x. So the rest of the function is actually represented by dv, ln x dx. And to get v, remember, you take the integral of dv, which is ln x, the integral of ln x dx. So every time that you're given an integral where you will utilize the integration by parts method, basically the first two things you're going to have to look for is the u and the dv. The u is going to be whatever the best choice is, and the dv would typically be the rest of the integral. So now let's use the formula, because the special formula is essentially the answer that you will get for the integral. So when you apply it, you may or may not know the actual integrals as part of the formula, what those integrals actually get. So we may or may not know what the integral of ln x is. And if we don't know, we have to apply the IBP process again. In this case, we'll apply it for ln x. So applying it, u will be again ln x, take its derivative, 1 over x dx. dv is the rest of it, so dx. Remember, the integral of dv is x. So now we do IBP for just this specific part, and that gets us this. In this case, we can actually compute this integral by canceling out the x's, and this is the integral of ln x. The reason we're doing this is because we have to substitute that into the original equation and finish off the problem. So doing so yields this. Simplifying it, we get this, and now we can actually solve this integral. And solving that integral will look like this. And finally, simplify. Now let's consider the following function. The first thing to note is the variable of integration. Even though we have two variables written, the variable of integration is y, because there's a dy. If it was dx, the variable of integration would be x. And since the variable of integration is y, we would treat x like it's just a constant, a regular number. The next thing to do is we have to rewrite this integral using the limit approach, because it's an improper integral. So we take the limit at its undefined points. In this particular problem, the function is defined everywhere except for at infinity. So we have to take the limit there, creating a dummy variable called a. Now we have to apply the hierarchy, isolate. And so the best choice would be y, because when you take its derivative, it leaves you with dy. And then dv would be the rest of the integral. Taking the integral of dv would give you this. Now apply the uv minus integral v du formula. In this case, remember that this is a defined integral. So the uv part is going to be defined as well, and only the uv part. Since x is a variable, we can move it out of the integral. Double negatives cancel out to be positive. Then we evaluate both pieces. Now apply the fundamental theorem of calculus. And remember that we can rewrite the negative exponents like this. This will be helpful later on for what we'll see will cancel out. Now you can apply the limit at the very end. Sometimes you can write the limit at every step, but I chose to apply it at the very end. So a is approaching infinity, so let the limit approach. Now the general rule of thumb is that the exponential decay decays faster than polynomial growth. So the first, negative infinity over x e to the power xa, that will actually tend to 0 because polynomial growth is decays much faster. So here's how it simplifies. Then finally, you get this. Let's now consider another example. The following function, being an improper integral, we have to apply the limit rule again. And now we're ready to run through the IBP process, taking u as e to the negative x, with its derivative being this, and dv as cosine 3x, with its integral being this. Then you have to apply the uv minus integral v du formula, yielding this as uv, remembering the principle about defined integrals, minus v du double negative gives you plus. Notice now that we have another integral where we have to run through the IBP process again. Running through that again, this time take u the same, du the same, in this case dv being sine 3x, and its integral being this. Substituting that into what we have already, uv minus integral v du yields this. Now, the trick here is to recognize that we have the same integral we're trying to solve for on both sides, on the left and all the way on the right. So we can isolate them and solve for it. First thing we need to do is distribute. Then, to first isolate it, we need to add both sides. Then, we can simplify this to this. From here, there are no more integrals, and we're actually ready to apply FTC to the right-hand side. Applying FTC, fundamental theorem of calculus, to the right-hand side would be this for the first part, substituting the top bound and subtracting the bottom bound, and then minus the second part, doing the same thing. Letting the limit approach would yield this. Remembering the same principle from the previous problem about exponential decay decaying faster than any of the trig values. And simplifying that will give you this. Notice that we have a coefficient of 10/9, which we would have to multiply by 9/10 to get rid of. And then we have the solution to our problem as this. Thank you for watching another edition of TutorTube. I hope this video helped. Please subscribe to our channel for more exciting videos, and check out the links in the description below, and follow us on social media. See you next time.